Hi. So let's see if I have any slides. OK, that's my name. I'm Michael Veale. I'm a lecturer, which is, like many things in Britain, Brit speak for assistant professor or other kind of things. At University College London, I'm in the Faculty of Laws. And I want to talk a bit about the trajectory I think, people and AI and AI in society, we reflect a lot, and we reflect a lot on problems of the past, and things like credit scoring, for example, comes up a lot. We've obviously had decades of thinking about credit scoring and some of the inequalities it causes and some of the systems that have underlied it. However, going forwards, where are we going technologically, and where do we have to put our focus to ensure that actually these technologies work with and for people, not in tension with them? So I want to talk a bit about privacy-preserving technologies and machine learning. And I want to talk a little bit about how that's developing, the trajectories there, some of the promises that it holds, but also some of the tensions that I think we're not grappling with quite as explicitly as we could be. And the broad argument I want to make is this. We've got a new flavor of privacy-enhancing technologies. Some people call them PETs. And what these do, these effectively separate out optimization from the data. So traditionally, we've thought of data giants, so Google obviously being one of them, who have hold a lot of data about individuals around the world and can use that to build interesting products. Like, I mean, some of the decision support stuff going on behind me is interesting. And those are great. But they always required centralization of data. And these technologies say, actually, to make products or to deliver profiling or personalization, we don't have to be near the data at all. And in fact, we can be in a position where we can mathematically say, we can't even see the data, even if you come to us with a warrant. So this is interesting, because this actually allows detailed optimizations of the kind that are carried out today to be carried out in a confidential way. And that's confidential in relation to the company that may be orchestrating them. And that's pretty good in an era of pretty dangerous data centralization, not least because of the number of data leaks we're seeing. Many organizations that are being pressured to do more with data don't really have the resources to secure it, particularly in light of adversaries who want to get hold of it. However, I also want to emphasize then that confidentiality is not a linear path to good technology, because actually even confidential technologies can be configured in ways which are not really great for people. They're not human-centric. And it gives a license to maybe do a bit more with data, and it gives a license to use it in a bit of a freer way, but it does not give a license to operate on all the things that might be mathematically possible. And particularly when we think of experimentation and manipulation, just because there's no information leakage doesn't necessarily mean we should be able to do it. So in order to kind of get at this, I want to introduce some technologies that will be familiar to some people in the room, but maybe less familiar to others. The first one is a technology called multi-party computation. People often call it MPC. And a secure multi-party computation is a protocol. There are lots of underlying building block technologies that can enable this. It can be configured in different ways. And it allows many individuals or entities to collectively compute an aggregate function over data they all hold pieces of. So they could be rows or columns. Think of it, they could hold either, without revealing what they hold to any other player or entity in this system. So there's two main setups we can imagine this working in. One of them is that we've all got smartphones. These will have data on, things like web browsing history or telemetry data. And we might want to compute some aggregate function. That could be anything from a simple sum or standard deviation to a machine learning model. And linear regression is a common one that's being used in these systems. And in order to do that, these devices can communicate with each other. They can send messages to each other. These messages do not reveal data to any other party, but the result of these messages being sent to each other is that an aggregate function appears. This is very, very computationally costly when you have even just a handful of users, or definitely tens of thousands and millions. It does not currently scale to. So another approach is that all the individual devices will secret share their information to two or more servers, that you just had to assume will not collude. If they colluded with each other, you could rebuild the data. But if you can firewall these organizations away from each other, you can actually say, well, no one can see the data in plain text, but we can still get some of the aggregate information from it. So these are the two main setups of multi-party computation. This is one of the building blocks. Another of the building blocks is called homomorphic encryption. And homomorphic encryption effectively is a type of encryption which retains its structure when it's transformed. So when we encrypt data, we usually can't do much apart from decrypt it. do a few things, but not really, for normal types of encryption. However, homomorphic encryption can be added or multiplied, and the result of that later decrypted. And this allows you to encrypt information, send it to a cloud service that is not unable to see it. The cloud service can then run a protocol to transform it. You can get the result, and you can decrypt the result. But the cloud service could not see what the data actually was that it was being operated on. So that's another building block of these technologies. A third building block, these are called trusted execution environments. Many of you will have one in your pocket. They effectively are a tamper-resistant, separate part of a computer, and they guarantee the authenticity of executed code and various other interesting guarantees. And these enable you to actually slot these in ways to make bigger protocols function. They have many different roles, fingerprint sensors, for example, being one of them in many cases. Another building block is called a zero-knowledge proof. Now, this, for some people, is really black magic. A zero-knowledge proof allows one actor to prove that a certain process, policy, or procedure was carried out, or a system displays a certain property, without actually needing to reveal any information about how that property was known, or even what the policy, process, or procedure is. There's a common example here about how zero-knowledge proofs work, and our old cryptographic friends, Alice and Bob, Alice goes into a cave, and Alice knows the secret password to a magic door at the back of the cave. She wants to prove to Bob she knows this password, but she doesn't want to tell Bob what it is, or even tell Bob really much at all, frankly. And so basically, without Bob looking, she goes down one of the two routes, but Bob doesn't see. Bob then shouts a route that she should return from, and she does so successfully. And if this happens multiple times, because Bob has got the choice of which route to call her back from, statistically, you can show that she knows the password. And this is one of the conceptual building blocks of zero-knowledge proofs. And of course, this doesn't sound so useful, but as a building block, we can do quite a lot with it. So these are the building blocks here, and there are different structures. So the structures I've talked about here are the edge structure, where users calculate among themselves, or the non-colluding distributed structure. And those are two ways of doing this. So why am I introducing all this, especially an area of AI? Because it's got interesting applications. And we need to kind of think about these. So when we see them in the wild, there's not a huge number of them in the wild, but we can see a range of ways in which they can be used. So a common example of how these are used is an old example from Aarhus University in Denmark in agriculture. And this is, I see people nodding. Some people have seen this before. A challenge to, I think by Thailand and Australia actually, to EU sugar beet subsidies. Yes, they do grow sugar in Denmark. By the World Trade Organization meant that Denmark needed a more efficient market, because Denmark doesn't actually grow sugar that efficiently. And they needed to find a realistic market price for this. And so they wanted a nationwide double auction to see how much could the farmers provide, at what cost were they able to do so. But the farmers find this very sensitive information because it reveals something about their productivity. They feel they could be manipulated in the market, particularly because there's only one buyer of sugar beet in Denmark. It's a monopoly buyer. So they didn't want to reveal this information, but they're happy to see what the clearing price is. 80% of them were really worried that this productivity data would be exploited. So effectively, with Aarhus University, there was a multi-party computation that was carried out where the farmers could provide, in economics terms, their supply curve, and the single monopoly buyer would provide its demand curve, and the market clearing price was worked out without anyone having access to this data that was so sensitive. So that's cool because it enabled something to be done that there was a social friction, but everyone wanted to be done. So that's a really nice example of where we can use these. So obviously, this is a Google event, so it would be bad if I didn't give a Google example. Google is, in terms of revenue, an advertising company. We don't really mention it too much in this room, where people are doing really interesting stuff, but this is where the money comes from. And one challenge that Google has, and this is all public and publicly written about, is that on small screens, or maybe on billboards, we don't know really the conversion rate for adverts of certain types. So for example, if you see an ad, a banner ad for Coca-Cola, you're probably not going to click through and buy a Coca-Cola within an app and have it sent to you. And if you see a banner ad for a Land Rover, you're also probably not going to click through and buy it. So there are certain types of ads where it's very hard to work out what's being spent and by whom. So in this case, we've got Google that knows what individuals saw, or even what they clicked on, but they don't know what they spent, and they want to know the effectiveness of these ads. A MasterCard, however, knows what individuals spent, or at least many individuals. What if you could join the two? And so this is what's happened. So there is basically a secure set intersection, which uses multi-party computation, homomorphic encryption, to do this. So Google has the information about who viewed an advert and which advert they viewed. MasterCard has had who bought a product and how much they spent. But to actually collect the data and centralize it would be illegal in many jurisdictions and would probably be very uncomfortable. Together, Google wants to see how much money people who saw an advert spent on that advertiser, an aggregate result per campaign. So this result pops out, this interaction between these two parties pops out this result. It says that for this Coca-Cola campaign, people who saw it in total spent this much. So this seems interesting. But we should also pause a second, because I think this is clearly motivated by a valid and interesting business case. Advertisers want to know their performance. But would it be OK if this wasn't spending data, but it was health data, for example? Would it be OK to say, I want to see how many people with a certain health condition clicked on this ad, or how many people with a certain health condition use my product in this way compared to another way? If we say that this is the free-for-all, and actually querying data to find out anything at all is a free-for-all just because there was no confidential information about any one individual, I think we're in problematic territory. I think reflecting on it, we can see examples where that would make both us in this room a bit queasy, and definitely, I think, the general public a bit queasy. This is really a form of informational power, because knowing things about populations is a very powerful thing to do. They're very powerful sets of information. So I want to leave that and to think about there. The last example I want to give is around local personalization. So again, the way that adverts are delivered is still largely in a centralized model with profiling happening on a central server. And local personalization asks, let's do it at my place instead. So can we target users in the same way as before, but without any data about them leaving their devices? And I don't want to kind of go into the details of this, but in fact you can. Like there are conceptual ways that this is possible to do, that you can target on the basis of information such as your web browsing history on your device. And you could even make individuals have to target themselves and make other services, like cloud services, conditional on them doing so. So this is quite an interesting idea, and I think on one hand it solves the big centralized data problem, but on the other hand, what happens here? We have a bit of an inability to scrutinize how these systems work. There is a challenge to say, are individuals being manipulated here? Who is seeing what? We've already talked, and many people in the room work on issues of algorithmic bias, bias in terms of job ads, bias in terms of just exposure to information, and diversity of news sources, for example. And if we move this personalization onto devices, what happens in terms of the auditing? What happens to individuals' data rights and their ability to actually navigate and determine how they're being read? And some of this literature, the cryptographic literature, really assumes that we can know what's on our device when we're being analyzed. We can actually just say, I don't want to run that kind of code. I'm going to opt out of this protocol. And that would be your defense. But I mean, firstly, people don't have the time to do that. Secondly, both Android and iOS make it very difficult to understand the code that's running on your device, particularly within third-party apps, where it can be very hard to install and very hard to understand what code is running, and also even very hard for the developers of these apps to really understand what code their app is executing, because there are third-party SDKs involved. So I think we start to see these assumptions fall apart a bit, the assumptions of protection. And I think we have to consider very carefully, if we go down this road, which has benefits, and it has benefits in terms of privacy and confidentiality, it's not a free-for-all. What are the protections placed for users, societies, communities, and how should individuals be able to navigate what is running on their device? When we look at the cryptographic literature, we can see some worrying, motivating examples. There is a little bit of a genre in cryptography of motivating what you're doing with a social problem. And say, hey, our protocol solves this challenge. And here's one of them. That's no. Can I? Yeah. I'm going to ignore that notification. Sorry, can someone click that off? Is that OK? About 25% of high school freshmen fail to graduate from high school on time. So to mitigate this problem, we'd like to be able to predict at-risk students and propose the right intervention for them. Students might drop out because of health conditions in her family or because of their welfare state. Therefore, making accurate predictions requires integrating data across different institutions, schools, hospitals, welfare systems, police departments, and more, and then it proposes homomorphic encryption to do that. But is the problem here that these organizations are seeing the data, or is the problem the risk scoring? And there's a bit of a category error going on here, I think, again. I'm not the first person to observe that cryptography can be configured in ways that are not conventionally good for individuals. Philip Rogaway, after the Snowden revelations, wrote a really interesting piece, pretty short piece, called The Moral Character of Cryptographic Work, where he says, I think correctly, that because cryptography gives individuals, even on their phones, the ability to encrypt text in such a way that even a state-level adversary cannot intercept and intervene, we assume it benefits the weak. And in many cases it does, and it allows us to create systems that benefit the comparatively weak, but it can also be configured in ways which do not benefit the weak. It can be configured in ways which can realize arrangements of power that don't trivially flow from the nature of the tool. One old example of this is in copyright. So copyright is a very finely balanced set of laws. I mean, people will argue if it's balanced in whose favor, but it has exemptions, things like fair use or parody or satire. But digital rights management tools, and also tools on YouTube like Content ID, are pretty blind to these uses. And they don't respect the balancing act that the law has put in, because Content ID on YouTube can't detect when music is being used to parody an artist or when it's being used to put behind some video without paying a royalty on it. But those are very different legal categories. So that balance, because of effectively, Content ID is not cryptographic, but DRM tools obviously were very problematic. And you saw this as well with DRM being applied to works that were out of copyright, for example. And that was not being respected because just because something's out of copyright doesn't mean you suddenly get the decryption key. So this is an interesting balancing test that's going on here, and configuring that is really important. So a few points I want to end at here. Firstly, we do need to draw a bright line between privacy as confidentiality and informational power. They're both things that we and populations and communities care about, and they have got overlaps, but we have to navigate them also somewhat separately, because one doesn't help the other necessarily. So that's really important. There are real societal dangers of legitimizing what you could call a ubiquitous query system. Just because this data is accessible and you can ask any question of it while respecting the confidentiality of every individual doesn't mean you should. There are many questions which, like in research ethics, we would say probably you should be getting some thought about whether you should be asking that kind of question and who has the right to ask these kind of questions. And this is really about infrastructure. So it enables huge information asymmetries, which both companies can use in pretty nefarious ways, but also worryingly, which states can co-opt. If you build this system, states might say, OK, well, give me access to Mr. X's data. And they say, we can't, not mathematically possible. And they, OK, well, instead, tell me all these things about this population. Make people run this code on their device to analyze what they're doing. And these are concerns that you still get new forms of power that emerge. So data processing must be legitimate, not just confidential. I think users must have practical visibility and control over the code running on their device, and that's not happening right now. We've got a lot of cloud services. We should really consider whether they can or should not be made conditional on users running this kind of analysis, profiling themselves. Particularly because there is a temptation to say, just because it's confidential, it can be more invasive. Hey, upload your health data, upload your walking data, upload your location data to your phone. We'll use it to target you, and we'll use it to personalize things about you. But we're not going to see it, so it's fine. There is a bit of a creep that can go on here, and I think we should consider the trust issues that can happen in this creep. And experimentation on individuals, A/B testing and so on, is still experimentation. If you're running a dating service, and you're trying to understand matching people with other people, and you want to effectively show people different populations compared to someone else to try and find out which people are attracted to who else, that's experimentation. It doesn't matter if you're doing it in a confidential way. And when we look at research ethics, we don't look at personal data as a trigger to triggering research ethics. We look at the involvement of human subjects. And this is the involvement of human subjects, even if personal data is not around. But legally, I'm in a law faculty, and data protection law is quite interesting in this way, because data protection law does not require that you actually have access to the personal data to be considered a data controller. We have 3 cases from the European Court of Justice around this. 2 are about Facebook and German companies, and one of them is about Jehovah's Witnesses. which is obviously a happy bedfellows, these three cases. But they're very interesting because what they do is they say there's a role of orchestrating actors in taking responsibility. If you are incentivizing data collection and you're benefiting from it, even if you can say, oh, I can't see it myself, you're still involved in this process legally. But do the tools match the job? Do rights of access, erasure, objection really work on local devices or mobile phones when dealing with embedded AI systems? Of course, the other thing in many people's pockets, phones increasingly have a lot of edge computing power. Both Google and Apple have invested quite heavily in architectures that run machine learning models on device. And Doug was talking about this a second ago, and they can have great, cool effects when people want to do edge computing and customize models themselves. But they also can have other effects. And so we're building a system where this is possible, and we have to consider. Lastly, my last slide here, we need to focus on infrastructure in law and policy particularly. I mean, this is really what the question I think is often about. If we focus too much on models or analytic products, we miss actually big infrastructural questions. There's a lot of AI ethics documents going around, and one thing that's absent from almost all of them is infrastructure. The ability to optimize, the ability to reach and experiment and get this data on a continuous basis, the ability to deploy models, the ability to even train in confidential ways. Google is just one of companies that has embedded trackers covertly on not quite a majority of websites, but a significant proportion. I think it's about 30% depending on where you go in the world. This is an infrastructure, and we have to consider the role of infrastructure in AI and the role of infrastructure and trust in AI, because they're very, very linked. And if we separate them, we're not really doing justice to the problem, and we're also not going to get a trustworthy system, because we can say you're running a model that's debiased and, hey, it's blind to whatever protocol or whatever characteristics you want to talk about. But you've actually got an infrastructure that is able to manipulate people and to track people, then I don't think it's going to undermine the great work that's being done elsewhere. So these are linked, and I know it's challenging within companies to go and talk across these boundaries, but I would really call that be done more. So thank you very much.